Welcome to the Explainer. Today, we're taking a pretty wild ride. We are going from the massive, explosive forces of a rocket launch all the way down to the microscopic sensors hiding right inside your pocket. So let's jump right in and demystify this incredibly cool piece of tech known as the accelerometer.
Have you ever turned your phone sideways to watch a video and the screen just perfectly rotated along with you? It kind of feels like magic, right? But how does your device actually know which way is up? Well, that tiny little piece of everyday convenience relies on some seriously impressive hidden engineering. To really get how this works, we have to talk about motion first. Think about a snail moving along a path at a completely steady, constant speed. This is linear motion without acceleration. Sure, it gets the snail from point A to point B, but from an engineering perspective, it's pretty straightforward and, let's be honest, kind of boring.
Now, contrast that slow, steady crawl with a literal rocket launch. We're talking pure, explosive acceleration, a rapid, intense change in speed and direction. Measuring these extreme forces isn't just fun to watch, it's absolutely crucial for modern engineering to keep these multi-million-dollar machines exactly on track.
And really, the big takeaway here is that accelerated motion is what makes the world so interesting. Whether it's the lightning-fast strike of a chameleon's tongue or the rapid, hovering wing beats of a hummingbird, dynamic motion is literally everywhere. And we need a way to capture and measure those changes, both in nature and in our own technology.
Section 1. The core concept. What is an accelerometer?
Simply put, an accelerometer is a sensor designed to measure accelerated motion and the force of gravity. If we strip away all the complicated physics equations for a second, this device basically answers two fundamental questions for us. How fast is my speed changing, and which way is gravity pulling me?
But here is the real puzzle. It makes total sense that you could bolt a giant bulky sensor onto a rocket ship to measure those huge forces. But how in the world do you fit a motion tracker capable of that kind of precision into a watch? How do we shrink literal rocket science down to fit onto our wrists?
Section 2. The microzoom. Inside the MEMS sensor. Welcome to the wild world of MEMS. That stands for Micro-Electro-Mechanical Systems. It sounds like a mouthful, but it basically just means we are building microscopic mechanical parts, actual moving physical structures, directly onto tiny silicon computer chips.
When you see the colorful schematic right next to an actual electron microscope scan, it proves this isn't just some theoretical math. This microscopic engineering is absolutely real. You're looking at physical, moving parts that are a mere fraction of the width of a human hair. So, let's break down how it actually works. On the outer edges, there's a fixed support structure anchored permanently to the computer chip. And it's designed with a specific sensing axis, meaning it's built to detect motion moving back and forth along one single, very specific line. Then, suspended right in the middle, you have the proof mass, which includes these tiny interlocking fingers. It hangs on microscopic springs so it can move independently. Think of it like being a passenger in a moving car. When the driver slams on the brakes, you jolt forward against your seatbelt, right? Well, when your smart device accelerates, this microscopic mass shifts inside the sensor in the exact same way. It all happens in a really elegant three-step sequence. Step 1, the device itself accelerates. Step 2, that internal mass shifts on its tiny tethers because of inertia. And step 3, this is the real genius part. As those microscopic fingers slide closer together or further apart, the electrical capacitance between them actually changes. We are literally translating a physical mechanical movement directly into an electrical signal that a computer chip can read in an instant. Section 3. Making it real. Everyday applications.
Because of this design, these tiny MEMS accelerometers are absolutely everywhere. They're the exact same microscopic mechanisms deploying your car's airbag in a fraction of a second during a crash. They're flipping your phone screen, they're tracking the tilts in your game controller so you can steer a virtual car, they're even monitoring the acceleration of the elevators you ride in so you don't spill your coffee. It is just incredible versatility from one tiny sensor. And their sensitivity is totally off the charts. Accelerometers are actually precise enough to track massive tectonic shifts and surface waves during earthquakes. So we're talking about the exact same technology concept scaling from a tiny chip inside your phone all the way up to measuring the rumbling of the earth beneath our feet. But they don't just measure the Earth's vibrations, they can measure ours too. Take seismocardiography. It's a big word, but the concept is just awesome. These sensors are so incredibly delicate that when placed on a person's chest, they can literally detect the tiny mechanical vibrations of the human heartbeat from the outside. They are feeling the physical thud of your cardiac cycle.
Which brings us all the way back down to your wrist. This unbelievable MEMS technology, the exact same principles tracking earthquakes and saving lives in car crashes, is sitting quietly in your smartwatch right now, tracking your steps and monitoring your workout form all day long.
And that leaves us with a pretty thrilling thought to end on. We've gone from the explosive acceleration of rockets down to microscopic silicon fingers tracking your pulse. So as MEMS technology gets even smaller, cheaper, and more precise, what invisible forces are we going to measure next? I hope next time your screen rotates, you picture those tiny interlocking fingers working away inside. Thanks for joining me for this explainer, and keep questioning the incredible tech hidden right in front of you.